interstitial heat transfer coefficient and the interstitial specific area density actually are shown in this two figures 10 and 11. So we wanted to see the effect of porosity and pore density for these two vital parameters. So this, by doing this analysis, we came to know that okay, now at this point of time we have to consider the porosity and pore density, and then we should see how it affects the surface area density and the interfacial heat transfer coefficient. Now if you see the interfacial area with respect to the porosity, now when porosity increases, what will happen to the interfacial specific area? So you can see, for by varying the pores per inch, in this analysis we have considered the variation like 5 ppi, 10 ppi, 15 ppi, 20 ppi, 30, 40 and 45. You can actually ask me how you have decided the range. We have considered the results in the literature, and in literature they have considered for porosity. To decide the porosity, we have referred the literatures, and then we considered 0.8 to 0.97 porosities. Then if you see the effect of the increase in porosity on the specific surface area, for example, when porosity increases, you could see the ASF interfacial specific area, it decreases. So this is one main observation. So for different PPIs, it has been reported here. For 40 PPI, the surface area is going to be more. So you can see the highest value for the 40 PPI, whereas for 5 PPI, the specific area available surface area available is more. So but when porosity increases, this trend is going to decrease. Whereas for 5 PPA, this is what we have observed when we performed our simulation. Specific area then moving on to the porosity more. So when the specific area surface area, when it is analyzed with respect to the pore density PPI, by changing the porosity, when it increases for different porosity, you could see the increasing trend. In the previous case, we are seeing a decreasing trend. In this case, we are seeing a different trend, like increasing trend. But for the 0.8 porosity, we are seeing more ASF when pore density increases, whereas for 0.97 it is lesser than the 0.8 porosity case when we increase the pore density. And this is the case for the interfacial specific area. Now what happens when porosity and pore density are increased? What happens to the convective heat transfer coefficient? So that is given in the next slide. So here you can see the variation of the heat transfer coefficient with respect to porosity and variation of heat transfer coefficient with respect to the pore density. Now when I say heat transfer coefficient, it is actually interfacial heat transfer coefficient, which is associated in the LTNE model. Okay, so this is now showing increasing trend for both the cases, for the porosity as well as the pore density. So when we increase the porosity and when we see different pores per inch, the interfacial heat transfer coefficient is high for the 40 ppi case compared to the 5 ppi case. Similarly, when we see the heat transfer coefficient with the increase in pore density, we could see 0.8 porosity is having a lesser interfacial heat transfer coefficient compared to the 0.97 porosity. So the trend, if you see for the surface area density and for the interfacial heat transfer coefficient, they are actually following a different trend. In the previous case, you can see with respect to porosity, the specific surface area is decreasing, but with respect to pore density it is increasing. Whereas in case of the interfacial heat transfer coefficient, it is actually increasing for both the cases, porosity and pore density. So then we realized that the variations of the thermal and hydrodynamic performance of metal forms not only depend on the structural properties alone, but also on their various combination. These various combination have to be figured out. So that is the highlight of the present work. Now, when we see the heat transfer coefficient, we saw increasing trend. But when we, on the other hand, if we consider the friction factor, now this friction factor is showing a different trend with respect to porosity and pore density. The friction factor is now decreasing with the increase in porosity, but for the 40 ppa case, it is showing higher friction factor. But for 5 ppa case, it is showing the lesser friction factor. On the other side, if you see, with respect to pore density, there is an increasing in trend for the friction factor. For zero point 0.8 porosity, you can see the friction factor to be more, and then for 0.97, the friction factor is less compared to zero point 0.9 when there is increase in pore density. So now we thought, at this moment, at this juncture, we thought we have to consider both the parameters like the heat transfer and the pressure drop, because they are showing different trends. So in that case, one has to define only multi-objective objectives. One is actually enhancement of heat transfer. The other one is minimizing the pressure drop. So at this juncture, it is clear that we are going to deal with two objectives. One is the maximizing heat transfer. The other one is minimizing the pressure drop with respect to these structural properties. And even if you see the Nusselt number, wall Nusselt number, you could see increasing trend for the porosity and the pore density. So Nusselt number increases with increase in porosity because of the increased availability of fluid to carry heat. Increase in wall Nusselt number with pore density is due to increased interfacial specific area of the foam structures. So in this moment, we are considering these two objectives, but it will be stated as one objective, which is nothing but the multi-objective. So that multi-objective contains the maximization of heat transfer and minimization of the pressure drop. So now when we figured out this, and with respect to the porosity and pores per inch, when we analyze these two, how do we represent? That is very important. How do we represent these effects on the heat transfer and the pressure drop? So when we looked into the literature, then we figured out this Topsis method. This Topsis method is used only, it has been extensively used in the manufacturing and other sectors. Very less number of literature is available in the case of heat transfer. That's why we started off thinking to apply this Topsis method for the heat transfer, to find out the heat transfer characteristics. So now let me introduce this Topsis method. So this Topsis method is actually nothing but a technique for order preference by similarity to ideal solution. So here we are going to talk about in the linguistic term. So for example, the decision maker, he will decide the solution. So for instance, in our case, it is maximizing and minimizing the heat transfer flow resistance parameters respectively. So the decision matrix is going to be in a linguist term, and then the decision maker is going to decide what kind of parameters are involved, what kind of weightage is associated with these parameters, and finally he will come up with his own decision with the maximizing and minimizing the given conditions. So it seems to be reliable for different cases. People have applied for different problems in the manufacturing sectors and even other fields. and then we found out this is quite interesting. So we applied in our work. Basically, we are going to deal with the sorting of the parameters, then selection and arranging the cases based on the desired parameters. And then we are going to figure out the ideal solution based on the closeness of its proximity, uh, 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 whether it is beneficial or non-beneficial, and then accordingly the weights will be distributed. Then minimization or maximization of the objective takes place. So here, as I said here before, the user is going to decide everything. He is going to decide everything, and in fact, he will get eventually he is going to get a set of solutions, and then he is going to decide what kind of solution is favorable for him. And in our case, of course, we are dealing with a Nusselt number and friction factor. So we are going to maximize Nusselt number and minimize the friction factor. So let us move on to the steps involved in this. These are all very simple steps. If you read these steps, it will be very, very easy for you. For example, if Xij are the Xij is the parameters, then we want to normalize. For example, when some parameters is given to you, so it has to be like normalized. For example, if you consider a Nusselt number, or if you consider a heat transfer coefficient, then you can have different set of values in that this heat transfer coefficient, and then we have to normalize this. So that is actually being done in the first step. We are going to normalize. So normalization is done like considering one value in the numerator, and by dividing the numerator with by summing up all the values of Xij, and then squaring, and then taking a square root. The next one is, as I said previously, the desire is going to the user is going to decide the solution. So he is going to assign some kind of weightage to his desirable parameters. So he is going to assign some weight. Now that weight is multiplied with the normalized value. That is what being done in the step 2. Now step 3, the user is going to calculate the worst solution and best solution for the given matrix. Now, how do you select the worst and best? For example, maximum Nusselt number will be best value for me, and in case of pressure drop, minimum pressure drop is going to be best value for me. So I am going to classify this as a beneficial and non-beneficial. So I am classifying heat transfer to be Nusselt number to be beneficial, and the pressure drop to be non-beneficial. So in beneficial, I want more value of Nusselt number. In non-beneficial, I want very less value of pressure drop. And then I am going to calculate the Euclidean distance from the best and worst solutions. So that is treated as Si plus 1 and Si minus 1. And at the step 6, we are going to calculate the performance. So performance is going to be based on the Euclidean distance with respect to Si and Si minus and Si plus. So these are the steps. These are very, very simple steps. You can easily understand. So everything is in the form of matrix. When you apply, it is in the form of table. When you apply all these things, it can be easily converted into the performance score. So for illustration purpose, since we have time, how much time we have? So since we have time, let me illustrate one example, and then I will emphasize how we have applied this Topsys method for our research problem. It will be easy for you. So for example, Q, you can consider Q to be heat dissipation, and the relationship is given with respect to velocity. This particular problem has been taken from the second version of the optimization book from written by Professor C. Balaji, who was the chief guest for the today's program. So in his second edition, this Topsys method is explained very clearly. So we have taken up that one, and then we analyzed that problem. Then this one was applied to the research problem. So the same problem is stated here. So Q is going to behave with respect to the given velocity, like this equation, and the pressure, pumping power, it is going to behave with respect to the given equation, and V is going to be the velocity in the meter per second. Now, the idea here is to maximize Q and minimize P when we have various values of V. That is going to be the objective. And using TOPS is how we can proceed. For example, we have considered 10 different values of V, and these V values are substituted in the P equation and Q equation. P is the pumping power and Q is the heat dissipation. So P represents the second column, Q represents the third column for different values of the velocities. Now, here I am going to consider Q to be beneficial parameter because I want enhancement of heat transfer or more heat dissipation. So I consider beneficial parameter to be Q and non-beneficial parameter to be P. I don't want P to be more, that is pumping power to be more. Hence, I consider this to be non-beneficial parameter. Now, in the fourth column, we are doing normalization according to step 1 of the Topsis algorithm. So what I want to do, in fact, the second column, it is now squared, and then the last column will give you the summation. Then the normalization takes place. So the fourth column and fifth column, it is simply making the square, and the sixth and seventh column, they are actually in the normalization which was proposed in step 1. So normalization of the pumping power and normalization of the heat dissipations are shown there. Now the last two column is going to denote the weight. Now you can see here below the non-beneficial and beneficial Q, we have assigned weights to be 0 and 1. So the non-beneficial parameter is P. So we are giving it is an arbitrary thing. We are starting with 0. So it says that I am giving a 0 weightage to the non-beneficial parameter P, pumping power, and then I am giving maximum weightage to the parameter heat dissipation Q, that is 100% weightage, which is denoted as 1. So if you multiply the value of the normalized parameters of P with the weight 0, then it becomes 0 for all the values. That is what last but one column says. When you multiply with the weight 1 for Q, the normalized value of Q, then the same value is going to appear in the last column. And then we can calculate what is V plus and V minus according to the algorithm proposed in the Topsis. Now, when we do like this, we are going to calculate the ideal best solution and ideal worst solution, and then we are going to calculate SI plus and SI minus. They are the Euclidean distance based on the ideal best solution and ideal worst solution. Now, eventually, we want to report this in terms of performance chart. That is what in the performance parameter. PI denotes the performance score. Now, looking at the final column, PI is nothing but SI minus divided by SI plus and SI minus.
You can continue.
Hello? 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 What happened? Hello?
Sir, you can continue, no problem.
Okay. Thank you, Dr. Kondareddy. So in the performance score, you can see, for example, the highest performance score is assigned to 0.99. That is at the last row. You can see 0.99. That is which refers to the Q value and P value of 4.8041. It is actually quite obvious because we have given zero weightage to the pumping power and then 100% weightage to the heat dissipation. Let us see the different weightage now. If I give equal importance, 50% importance to the non-beneficial parameter pumping power and 50% importance to the heat dissipation, now our solution is going to change. When you carry out, when you follow the same methodology and when you do the performance score at the end, you are going to get a different value. For example, in this case, we are getting 0.5887 to be the highest performance score among the value given here. This refers to the fifth case where the beneficial parameter is now going to be 31.908 for Q and non-beneficial parameter is going to be 2.628, which is different from the previous case. In the previous case, we have given 0 and 1 weightage for the pumping power and the heat dissipation. Here we have considered 50%, 50%, 0.5 for the pumping power and the heat dissipation. So the solution is getting changed. Now, why I am emphasizing this? Because I am the user. Now I am going to decide how much weightage I can give according to my convenient and what solution is going to be suitable for me based on this analysis. This is how the Topsys methodology is very useful for the analysis. That's how we actually figured out and then we applied this to the research problem. So when we can also vary the weightage. You can even give 100% weightage to the pumping power and 0% to the heat dissipation, and you can carry out the analysis. So now I want to relate this methodology to the existing the research work. So in our research work, we have considered maximizing NU and minimizing the friction factor. So we have defined 5 criteria. So first criteria, which has 0 and 1 weightages. So 0 is for Nusselt number, 1 is for the friction factor. That means 0% weightage to the Nusselt number and 1 percentage weightage to the friction factor. Like that, we are going to increase the weightage, and then we are going to see how it affects the performance. So so at the end, what is important is performance chart is very, very important. So this performance chart will give you very good insight about how does the Topsys method work and how does the other parameters actually work when we have multi objectives. So for example, this performance score with respect to foam samples, we have considered different samples: 5, 10, 15, 20, 30, 40, and 45. Among 5, when we consider 5, we are also varying the porosities. Porosities varied from 0.8 to 0.97. So when we vary like this for different PPAs, you see the performance score. When we assign 0% weightage to the Nusselt number, when we say 100% weightage to the friction factor, so the preference is going to be 5 PPA. For any given porosity, you can choose 5 PPA metal foam, 5 PPA metal foam, when we are actually concentrating on the friction factor when 100% weightage is given. So for the range of given porosity for 5 PPA, so the friction the performance score is closer to 1. That implies that you can consider 5 PPA for your work when the desirable parameter is going to be only the friction factor. When you say no, I want to analyze in a different manner, I want to give a different weight. For example, if I consider 25% of the weight to the Nusselt number and then 75% of the friction factor, you could see now the solution or performance score is now moving towards a 10 PPA. Instead of 5 PPA, it now move towards 10 PPA. So for 10 given 10 PPA for different porosity, the performance score is slightly increased, especially for the porosities like 0.97, 10 PPA, you could see more performance score. So this is actually criteria 2. In the criteria 3, we are now giving equal importance. So I am giving 50% weightage to the Nusselt number and 50% weightage to the friction factor. In that case, now the solution moved toward 15 ppa. So for 15 ppa, still for 15 ppa at 0.97, the performance score is very high when 50% weightage is given to Nusselt number and 50% weightage is given to the friction factor. Similarly, when we give a 75% to Nusselt number and 25% weightage to the friction factor, the solution changes to the 20 ppa, 20 ppa, and the performance score is higher for the 20 ppa, 0.97 porosity. And you can see here now for the 100% weightage to the Nusselt number. If I suppose, yeah, I am not worried about the pressure drop, I am much worried about the Nusselt number, or I am giving importance to the Nusselt number. 100% weightage is given. Therefore, the performance score is now moved to the 40 ppa because of more interfacial area, and then also 0.97 porosity for 40 ppa shows the highest value of performance score. So now now when we give importance to the Nusselt number, you can see 40 ppa with high porosity, that is important. 40 ppa with high porosity, you can see 40 ppa 0.8 porosity is also there, but then it gives less performance score, whereas 45 ppa with 0.97 porosity, it gives a higher performance score. So this gives you a very good insight about all these parameters which we have considered so far. And then the important parameters such as the pores per inch and porosity play a major role, and these combinations can affect the heat transfer and pressure drop very much. That's how we figured out, and then we have done the analysis. So with this, I want to conclude here. We have taken up a problem definition which is equivalent to the electronic cooling, and then this kind of metal foams and other things can also happen, can also be introduced to enhance heat transfer. So when we do so, the question here is what should be the role of the porosity, and what should be the role of the pores per density, or what is the combined role of these two for the enhancement as well as the pressure drop. So so in the numerical methodology, we have considered the numerical model equivalent to the one reported in the literature, experimental setup, and then we found the Topsis method is more suitable for this case, and we applied, and then we got the solution, and we have discussed elaborately in terms of performance score. So for example, we have considered 63 foam samples which have been reported in the literature, and based on that, we chose the porosity value ranges between 0.8 and 0.97 porosities, and pore densities ranges from 5 ppa to 45 ppa. So it is actually user desirable. User will decide how to what to consider and what not to consider. So these are the references, and then I am very much thankful to my research scholar, because this work was carried out by one of my research scholars, Trilok. In fact, this was funded by our SERB DST funded project, and Mr. Trilok did this work, and we have published this work in the International Journal of Thermal Sciences, and he also helped me to make all these slides, and we had several discussions to come up with this research. And also I am very much thankful to all of you for your listening, patience in listening to this lecture. Special thanks to the organizer, Dr. Konda Reddy, and his team. Thank you, Dr. Konda Reddy. Over to you now.
Thank you, Dr. Gnanasekhar. Now the questions. Participants, you can start asking questions.
Hello, sir. Good morning.
Yeah, good morning.
Yes,
Who is this?
Hello. Sir.
Hello.
Actually, I have one doubt, sir. And you given a good presentation, sir. Nice. The presentation was very nice.
Okay, thank you
And
very much.
my doubt is, sir, how did you model the metal foam, sir?
Okay, so
Hello?
hello, is it audible?
Ah, yes, sir, it's audible.
Yeah. So if you have,
Hello?
uh,
Dr. Anand, please hold on. Question is clear. You can answer now.
Okay, sir.
is it audible? I think some noise is there, no?
Yes, Dr. Anand, Gnanasekharan, you can answer that.
Am I audible?
Yes, yes.
Okay. So, yeah. So, if a metal foam, how we model metal foam in the numerical model? That's what is a question.
Yes, sir.
Okay, so we have actually considered a fluid domain which is equivalent to the metal foam condition, and we have mentioned the porosity and pores per inch for the domain. We have mentioned this in the domain, and then all these values have been the pores per inch, and then the heat transfer, interfacial heat transfer coefficient, and then the surface area density have been calculated from the available literature, and these values have been given as input to the numerical model.
Okay, sir. Thank you, sir. And one more
Okay.
question, sir.
Yeah.
Sir, how did you implement LTNE method? Whether it is inbuilt in Fluent or it is just you have to write UDF or like.
No, LTNE, LTE model and all, it is actually based on the equations. For example, if you see the LTE model, then certain parameters are not required. When you consider LTNE model, certain parameters are involved. So for that, we have to specify accordingly.
Okay, sir. Thank you very much, sir.
Okay, ma. Thank you.
And
Thank you.
can I give you your email ID, sir? If some clarification,
Yes,
I can contact you, sir.
sure. I will request Dr. Konda Reddy to circulate my email ID to all of you.
Yeah, sure, sure.
Okay, sir. Thank you very much, sir. Thank you very much.
Yeah, thank you very much. Any other question?
Any other questions you can ask? In YouTube Live, 7 people are attending. If you have, you can ask you can type the question in the chat box. I will read the question.
You are not listening. Huh? You are not listening. Okay. Yeah, if they have any question, they can even write to my email.
Yes. Okay. If there are no questions, then thank you, sir. Thank you for sharing your research work on a multi-objective optimization study in the presence of metal foams for cooling of electronic equipment. Thank you for
Yeah.
accepting our invitation and attending for this session. Thank you, sir.
Yeah, thank you, Dr. Konda Reddy. It was a very good opportunity for us to showcase our research, and hope the audience enjoyed the lecture. If they have any queries, they can write to my email. Definitely, we will reply to them. Thank you for organizing such type of program, because it is very relevant and very important now.
Thank you, sir. Thank you.
Thank you very much.
Now, Dr. Tapan, are you available? Did you join? Just a minute. Dr. Tapan. It seems he joined. Just a minute. Yeah, right. Thank you. So let me introduce our session 2 speaker, Dr. Tapan Kumar Hota. Dr. Tapan Kumar Hota is currently working as an associate professor in the School of Mechanical Engineering, VAT Vellore. He has done his PhD in mechanical engineering from IIT Madras in the area of electronic cooling. His area of research in a broad sense includes active and passive cooling of electronic devices, heat transfer enhancement, optimization of thermal systems, thermal comfort modeling. Dr. Hotta has around 35 publications to his credit in journals and conferences of international repute. He has guided more than 30 UG students and a dozen PG students for their project work. Recently, 2 students have obtained their PhD degree under his guidance in the field of heat transfer enhancement. He has filed a patent on innovative design of PCM-based cascade heat sinks integrated with heat pipes for thermal management of electronics. He is currently the guest editor for the International Journal of Mechanical Engineering and Application for a special issue on heat transfer enhancement. He is a member of the editorial board and a reviewer for various international journals and conferences related to heat transfer. He is the recipient of silver medal for being the topper in MTech thermal engineering. He has received the travel grant from DST India to attend the international conferences held in Minneapolis, USA, Zurich, Switzerland, and Tokyo, Japan. Now I request Dr. Tapan to start this session.
So, thank you, Dr. Reddy, for the nice introduction. Am I audible to all of you?
Yes, yes.
Yeah. So, good morning, all of you. So, let me once again thank Dr. Konda Reddy and his team from IIIT RG UKT for conducting one of the need of the hour webinar. When you talk about thermal management of electronics, it is extremely important in the present scenario. Because it has to be addressed in a proper manner and it has to be tackled beautifully, and also we have to also overcome several challenges related to the thermal management of electronics. Okay, so let me share my screen now. Whether it is visible, Dr. Reddy? Dr. Reddy, whether screen is visible?
It is visible.
Yeah, are you able to see the screen now?
Yes, yes.
Yeah. So before formally starting the presentation, I just want to ask a couple of questions to the audience here. I think if I will ask you a question that how many of you are not using the mobile phones or maybe a kind of laptops, I think people will laugh at me, right? Because we are in a 21st century and life without a mobile phone and life without a laptop is, I think, we cannot think about. But if I slightly tune the question and if I will ask you that how many hours you spend in your electronic gadget in the form of mobile phone or the laptop. But now looking to the pandemic situation, our users to the electronic gadgets has increased because now living beyond the sleeping hours of 7 to 8, the rest of the time we are mostly dependent on our mobile phone or the laptops because we all are busy in either taking the online classes or attending the online classes. So I think the usage has gone up. But what is the challenge now? When you keep on using these electronic gadgets, they generate a huge amount of heat, and due to that, the temperature of the components rises, and that need to be tackled. Okay. So it's like our human body itself. You all know that, like our human body, suppose our body is getting heated up. What happens now? Either you come out of that hot sun, you go to a place where there will be a nice breeze so that your body will be cool. If that is not sufficient, you come and sit under a fan, or you go to a maybe a air cooler or air conditioner, And even that is not sufficient, you go for a shower. But shower is a kind of sprinkling arrangement. If you feel that that is also not sufficient, you know that in village we are having ponds and rivers. You go and completely immerse your body on that, so our body will be what, no, getting cool. So the same thing we are going to talk about in today's lecture. So basically, the title of the talk, I have kept it as hybrid cooling techniques for thermal management of electronic equipment. We'll see that what are the different techniques we are going to follow, and so that we can have effective cooling of the equipment. Okay. So what I will do here, if you have any queries, either you can put me, you can write down somewhere, or you can put that in a chat box, so that at the end of the session, we'll have a detailed discussion about that. Okay. Now, coming to the outline of presentation, this is the way I have outlined. I will start with what is the need of thermal management. Then I will go to what are the different techniques are available for the cooling of the electronic gadgets. I will just talk about a brief case study, and on that case study basis, we will discuss the 4, 5, 6, 7, whatever the outlines I have made here. That will be based upon a case study. Then I will just brief out how do you do simple experiments in electronic cooling. And we'll also see that how do you apply the optimization strategy in electronic cooling. Of course, Dr. Yanosakar has given a overall picture about the multi-objective optimization technique, but this won't be in depth here, but I will just highlight how do you carry out a simple optimization strategy in electronic cooling. Then we will see two extremely important cooling techniques. One is phase change material based cooling, as well as liquid cold plate based cooling here. Then I will summarize my talk. Okay. Now, as I told you that this is the need of the hour where thermal management is extremely critical, and the electronic components has to be cooled in a faster rate. Okay. Now, why this is necessary? Because if you can make a survey here, you can find that the electronic industries are increasing very, very rapidly. And why it is so? Because the use of the electronic gadgets are increasing in a rampant pace. And anything you see nowadays in engineering world, life without electronics is highly unthinkable. Okay? So that made the rise of the electronic industries at a rampant pace here. Now, not only the electronic industries are rising, what happens now, the component size also becoming smaller and smaller. Because if you can recall that if you go to a few years back, the kind of desktops and laptops you were using, they were quite heavy. But nowadays you can see, even if in a simple mobile, you are able to do all the steps what usually you are able to do in a laptop itself. So that means the size is becoming very, very compact. And also you can think that the kind of memory cards what used to come in a few years back, they were very, very lengthy and very not compact actually. But nowadays, even if in a small memory chip, you can store plenty of information. So there is a miniaturization now. The electronic component size is becoming reducing drastically. Now, what is if the size of the electronic components are getting reduced? This leads to increase in the power density. The meaning of power density is that the power requirement in the small size of the chips is increasing now, because you want to dissipate same power or even more power, but now the size is getting reduced. So this leads to increase in this power density. So ultimately what happens when the power density rises, the electronic components are going to fail. And it has been seen that the failure rate is exponential. If the temperature is not controlled below 100 degrees centigrade, then there will be exponential failure rate with this electronic components. Now, this pie chart has been taken from US Air Force Avionic Integrated Program, and you can say that apart from humidity, dust, as well as vibration, the major factor what causes the failure of electronic component is only temperature. So that's what I told you that there is an exponential rise of the temperature. The same thing you can also see from this graph, and you can see the graph between lifespan of the electronic components as well as temperature. There is yeah, so you can see the lifespan is proportional to e to the power of c by t, where c is a constant. This depends upon different parametric conditions, and t is of course the temperature of the electronic component here. So you can see there is exponential variation, exponential decrement of the lifespan of the electronic component with respect to what now temperature. And the research has shown that if the component temperature has increased by 10 degree, almost half of the life has come down as far as electronic components is being concerned. But now temperature increment is a usual business, like because if you talk about a laptop or mobile phone also, our mobile phones are loaded with a huge amount of apps, and so many gaming platforms are there in the laptops as well as mobile phone. And when you run these games, they generate actually huge amount of heat. Now, as we told that if the temperature is increased by 10 degree, there is a chance of a failure of your electronic components, either in the form of mobile phones or the laptops, and it has to be controlled. Okay. Now, let us see what is the objective then. So now we need to cool the devices, right? That is the first objective. You need a better cooling technique. But only cooling, whether it is sufficient? No. Apart from the cooling, we need to find out how do you arrange the elements of these components. Because if you see an electronic circuit, you can find that there are multiple chips are there. There are resistors, transistors, capacitors, heat sink. So many elements are being mounted on the top of the printed circuit board. Now, it so happens that if two high heat generating elements are placed close to each other, what they will do now, they will generate more heat. So it's always ideal to place a high heat generating element close to the low heat generating element. Then somehow you will be able to control the amount of heat generation from the electronic device. So that's why there needs the challenge of what? No, optimal arrangement. So you need to arrange the elements in such a way so that your heat dissipation rate will be what? No, controlled. Now, once you are going to arrange these elements optimally, there could be several arrangements can be possible. But out of the several arrangements, you need to identify what is your optimal configuration. Now, how do you decide the optimal configuration? There is a technique. That technique, anyhow, we'll discuss in our subsequent slides. But when you talk about optimal configuration, you just need to control the maximum temperature access. That means when you go for a particular arrangement of the elements, then you go for either experimentation or go for numerical simulation. You try to find out the temperature of each individual element, find out the maximum temperature of that configuration. But each device has been subjected to different ambient condition. So what you need to do now, that maximum temperature you need to subtract from that ambient environmental condition. So you need to get that maximum temperature access. That need to be controlled. So you need to choose the optimal configuration in such a way that the maximum temperature access will be far less. So you can say that your optimal configuration has been reached. So apart from cooling, this is also very important. Then only you are able to control the temperature in the case of what? No, electronic gadget. That's why you can say that many of your chips, they have been painted with black, because when you talk about black here, so we'll discuss about the effect of radiation. In black, what happens now? This will the emissivity will be close to 1. So in case of black, the temperature of the black pointed surface will be what? No, getting reduced. So these are some of the parts we need to consider. Then we can have the effective cooling of this what? No, electronic gadget. Now, looking to the cooling techniques, I can broadly you can say that there are two cooling techniques are available. One is active as well as passive. It's quite obvious when you talk about active, you need an external agent. You need an external agent for the cooling of the device. And when you talk about passive, this occurs naturally. Like I will give an example. You take your human body and you just go out, and by the nice breeze, when your body is automatically cooled down, that is basically a passive cooling. But instead of going out, what normally we do now, we spend a lot of money in the form of fan or air cooler or air conditioner. We sit inside the home. So that kind of a technique is known as what? No, active cooling, because you are using some external agent here. Now, under the active cooling technique, you can see we are having a forced convection air cooling, jet impingement cooling, spray cooling, refrigeration cooling, liquid cold plate cooling. All this, they need a pumping device, so that you are going to pump the either the water or the liquid water, so that the cooling will be more effective. And these techniques fall under what? No, active cooling. Now, when you talk about passive cooling, this occurs naturally when you talk about natural convection air cooling, thermoelectric cooling, heat pipe based cooling, PCM based cooling, or heat sink based cooling. Here, you don't need any external device in the form of pumping power. So the cooling occurs naturally. So they comes under what? No, passive cooling. Okay. But as a part of this discussion, I will just touch upon air cooling. Then we'll move on to passive cooling, PCM based cooling. Then we will talk about liquid cooling, liquid cold plate based cooling. So these are the three aspects I am going to talk about as a part of the present discussion is being considered. So, Dr. Reddy, is it going fine, or are you having any issues? any difficulty in listening to the talk?
Everything is fine. Your video, audio,
Oh, thank you.
everything is fine.
Yeah, thank you. So once you understood about the different cooling techniques, now let us highlight the different cooling methods, and you will see that how each method has its own pros as well as cons. Now, if you go back to years back, the mode of cooling is only air cooling. And but the only problem with air cooling is that it is only applicable to the low power electronic modules, where you can see the heat dissipation rate is only 50 watt per centimeter square, which is extremely low as far as the present electronic scenario is concerned. So maybe it can be used for personal computers with low memory power, CPU, GPU of smaller sizes, and low power rates, where you can see we are targeting a heat generation rate of 50 watt per centimeter square. Now the air cooling is being either you can go for a natural convection mode or you can go for a forced convection mode. But nowadays, lot of researchers has focused on the mixed convection mode, because in mixed convection we are going to consider both natural convection as well as forced convection. How is it possible here? Suppose same laptop you consider, and suppose you are just doing some typing work or some documentation work. Now during that time you can see the amount of heat generation is very low from the laptop. But in the same laptop, if you want to use for running a program which can run for around a couple of days, or if the same laptop you want to use it for gaming part, then you can see the amount of heat generation will be extremely high. So same laptop, sometimes you want a natural convection cooling, sometimes you want forced convection cooling, so you need a balance. That's why people thought that nowadays a lot of research is being going on the mixed convection aspect, where you can go to a higher heat dissipation rate up to what no 100 watt per meter square, watt per centimeter square. But now looking to the challenges of heat dissipation rate, when the heat dissipation rate touches about 1000 watt per centimeter square, like when you talk about cooling up data centers, IC engines, or large industrial systems, then air cooling may not be sufficient and ideal. You need to go to a higher cooling technique. So you can think about what now liquid cooling. But again, liquid cooling has a challenge because it's very difficult to handle the liquid. But we will see some of the techniques actually. How can you control or how can you handle the liquid so that you will be able to achieve a very high heat dissipation rate close to what now 1000 watt per centimeter square. But again, the challenge in the liquid is that what kind of liquid you want to use. Either you should go for water or some fluorocarbon liquids or dielectric liquids or nanofluids. So selection of the liquids is a greater challenge. But maybe in my next slides, I will just highlight that how do you go for the selection of the working fluid. So one criteria what comes to the mind is that high boiling point can lead to what no better heat removal. This we have carried out few experimental studies, and we found that if the boiling point of the liquid will very high, then what will happen if you go to the phase change diagram, the conversion from the liquid to vapor will be, this will occur at a very faster rate, because I think most of you must have studied about the phase change diagram. So in phase change diagram, what happened, the saturated liquid is going to convert it to saturated vapor. Now when you go to a high boiling point fluid, the conversion becomes much faster, so the length of that liquid to vapor conversion line, that will be getting reduced, so cooling will be what no, much faster. That has been seen experimentally. Maybe in the next slides I will just highlight upon that. But because of the difficulties in handling the liquid water, you can also think about phase change material, which is extremely common nowadays. And two important merits of a PCM is that it has got high latent rate of fusion. This can store huge amount of heat, and there is also uniform melting. So whenever, so this helps us to reduce the temperature effectively. And moreover, one more beauty is that it is recyclable in nature. You are not going to throw it out the PCM after use, because there is a conversion from liquid to vapor, liquid to solid, solid to liquid. It can be what no recycling. Huge applications. Either you can go for building cooling, either you can go for cylinder cooling, floodlight cooling, electronic equipment cooling. So these are some of the applications where actually the PCM is extremely used. So these are some of the techniques you can. These are some of the these are some of the techniques you can think about, but depending upon the requirement, depending upon the application, you can just see that which technique will be what no useful. Okay. Now, as I told you that I am just looking for a case study. Now, what we will do, looking to this case study, our entire discussion will follow now. And the case study what I have considered here, it's a switchboard power supply board, is SMPS board. I think this many of you must have heard about this SMPS board here. The main function of a SMPS board is that this converts the input to a what now output energy. Now, if you see about your laptop printed circuit board also, our input is you are giving the power input in the form of voltage as well as current. And finally, you can see the amount of work you are extracting from this what now the printed circuit boards. If you see that many components are being mounted. My printed circuit board, this is my SMPS board. Either you can call this to be SMPS board or a printed circuit board or a substrate board. All are synonyms. You can call it an any name. You can see these are aluminum fins are there. There is a MOSFET, there is a transformer, there is an inductor, capacitor, there is a transformer, there is a register, there are IC chips. So many elements are being mounted. So this is basically a complex structure. What if you think about the SMPS board or a printed circuit board? But with this complex structure, it is very, very difficult to carry out the experiments or numerical simulation. So what we have done here, so each SMPS board or each printed circuit board, this comes with a particular data sheet. So if you go to any electronic equipment, if you can open that, each electronic component has a kind of a data sheet. Now, if you go to the data sheet, all the components, they are either represented by a dot or represented by a solid line. That's what you can see from the right side diagram. So this is my actual SMPS board, but going to the data sheet of the SMPS board, I have converted into a line diagram. Now this line diagram depicts all the elements, whatever it is there in the printed circuit board. Now from the line diagram, you have to import into a CAD model. Now if you import it to a CAD model, why is it we are going to import into a CAD model? Because once you want to do the numerical simulation, each element has to be imported as for its identical entity. So this data sheet, now you have to import into a CAD model. You can see all the elements like transformer, resistor, capacitor, IC chips, all are being depicted in this CAD model. But now my objective is, when you look for the thermal management, IC chips are the only element which keeps on generating huge amount of heat. So their temperature need to be what now controlled. So what finally we have done in our laboratory, we have discarded all the elements like resistor, capacitor, transistor. Only we have kept the interest of this what now IC chips. So this is the way we have segregated from the SMPS board to a very simplified model. So we first started with a very complex model. We have gone to their data sets and we have converted that to a line diagram and dot diagram. We imported into a CAD model. From the CAD model, we discarded all the elements and we have only identified the IC chips, because the chips are only the heat generating elements. They generate huge amount of heat, temperature rises, and that temperature need to be what now controlled. Now in the present study, all this temperature, all these IC chips, I am giving by the symbol called U. U is basically a designation by the number of chips here. It has been 1 to 5, 1 to 7, you can see. So this is a very, very simplified model starting with this what now SMPS. Now let us see that how do you do a simple experiment as far as a laboratory scale is concerned. See, if you go to the actual printed circuit board, they are basically made by a material called FR4. FR4 is basically a reinforced concrete laminate sheets. And if you look to the IC chips, which is also otherwise known as a heat source or heating element, because they generate huge amount of heat, they are made by what now silicon. So in the laboratory scale, going for a FR4 board and going for a silicon chip, it is extremely costly, and this is also not effective to consider the IC chips as silicon and printed circuit board as FR4. So what you have to do now, you have to go for an idealization model without disturbing the thermal properties. So you have to maintain the same thermal properties. Now on that note, what we have done here, FR4 is basically a kind of board with insulating material. On the top of that, basically we give a copper coating that is basically conducting. But if you just look to the board, this is purely insulated. So on that note, the SMPS board, we are, you can say, we are mimicking by another closely relevant material called bakelite, because bakelite is also low thermal conductivity. Its conductivity is only 0.04 watt per meter Kelvin. Similarly, IC chips on an actual cell, they are made by silicon, and that again you have to mimic by one more material called aluminum, because almost the thermal conductivity is matching. Aluminum has got a conductivity close to 230 watt per meter Kelvin. But the chips could be either they are of a square size or they are of a rectangular size. Either they can be identical, they can be non-identical. Lot of work has been carried out on all these things. But in our present study, we are going to focus on non-identical rectangular sizes. Non-identical means whatever the chips we are going to consider, each chip has a different size, and also they are not square in shape; they are rectangular in shape. Okay. Now, once you do an experiment, what we need to do now, this silicon, we are now mimicking by aluminum. So you need to create that aluminum as a heating element. Now, how do you want to do that? Inside the aluminum itself, you need to make a small cavity. This can be done by milling. So once you make a cavity here, on that cavity, you have to put some heating element. You can see my heating elements is 80 by 20 nichrome wire. So inside that, you have to put some heating elements, but you need to take proper care because aluminum is metal and this heating element nichrome is metal here. There should not be any contact between two metals. So some Teflon tape you need to wrap up across this what now heating wire, so that there should be what now proper electric flow to this what now chips. Now these are my heater wires. They have to be directly connected to a DC power source. So now the aluminum chip, this can be treated as a what no heat source. And to measure the temperature, you have to mount some thermocouples. And in the present case, we have used a K-type thermocouple, which has got a very wide range from minus 22, you can go to close to 1000 degrees centigrade. So because of its wide range, most of the laboratory practices, K-type thermocouples are being used here. I'm not going to go to the details of this thermocouple part. Maybe I think you might have come across in the theoretical subject as well. But this is the way you are going to treat this aluminum heat source as a what now heating block. Okay. Now what you have to do now? Let us go how you are going to conduct simple experiments now. You see, this is my aluminum blocks. They have to get heated now. Once you want to heat that, you need a DC power source. So either you can go for a single DC power source or a multivariate DC power source, looking to your application, because it all depends upon that how many chips are you going to mount, because each chip you need to supply heat. Either the heat requirement for all the chips may be same or it could be different. So depending upon the application, you can choose the requirement of the DC power source, but the DC power source is only going to supply the heat to this what now chips. Now once the chips are getting heated, you need to measure the temperature. See, now manual measurement is extremely tedious. So what you need to do now, you need to record all the data by using a data acquisition system. This is called a data logger. So the data logger will directly read the temperature of each chips here. Then this will be stored inside the what now computer. So this is a very simple experimental arrangement. Maybe I think you can also do in your institute as well. Just take a chip, make it as a heating element, supply the heat by DC power sources, record the temperature by using data logger, then you can store the data inside a what computer. But now the challenge is, our objective is that you want to cool the chips, right? When you want to cool the chips, now let us go to energy balance and let us see that what are the different ways the heat can dissipate from the chips here. See, if you can just see about a simple chips, this is my inlet flow of air, this is outlet flow of air. This my board is made by what now bakelite. This is my aluminum chip. So what happens? First, you are supplying heat to the what now chips. You can see this is Q supply. This is the Q you are now supplying to the chips now. Now, once you are supplying heat to the chips now, chips are metal having a conductivity of 230 watt per meter Kelvin. Bakelite board, on the top of the bakelite board, the chips are being mounted. Bakelite board conductivity is 0.04 watt per meter Kelvin. So because of this huge gradient of conductivity, what happens? There will be huge amount of conduction heat loss may occur to this what now board. So there will be heat conduction from the chips to the what now board. But as the bakelite board is insulated, most or less insulated, because its conductivity is only 0.04 watt per meter Kelvin. So the Q conduction will be extremely small. But apart from Q conduction, also what will happen now? There will be heat dissipation in the form of convection, because the chips are going to cool. So they are going to dissipate heat to the ambient. Also, there will be heat loss in the form of what now radiation, depending upon the surface condition of the chips, whether they are polished surface or black surfaces. You can say that there will be huge amount of heat dissipation in the form of what now radiation as well. Now, once you understood about this heat balance, how do you do the analysis? Because once you go for the experimentation, as I told you that your main goal is cooling up the chips here. So this is the heat what you supply to the chips that can be calculated in the form of V into I. And this is a simple heat transfer formula you might have studied in your heat transfer course as well. Now, when you go to Q radiation, you can apply the Fourier's law. Sorry, epsilon emissivity sigma is the Stephen Boltzmann constant. A temperature of the ICC power 4 minus ambient temperature power 4, and this A is basically the frontal area of the chip from which actually the heat is going to lost in the form of what? No, radiation. Similarly, you need to calculate the conduction heat loss from the chip to the board. That can be calculated by using the Fourier's law of heat conduction. So conductivity of the substrate board, area of the substrate is how much area the chips are in contact with the board multiplied by temperature of the IC chips minus temperature of the substrate, thickness of the substrate board. Okay, this will give you Q insulation. But if you want to go for a perfect experimental setup, if you feel that still there is some amount of heat loss in the form of radiation, then you can use this error analysis here. First, you need to identify what is the error in the primary quantities. Then you identify what is the error in the primary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. Then you identify what is the error in the secondary quantities. By A into TIC minus what? No, T infinite, where A is basically area of the chip to the ambient. With this, you can find out this what? No, contribution of radiation. So why this is extremely important here? So more the contribution of convection, the cooling will be faster and the temperature will what? No, come down. But as it is a pure experimental work, so always when you do a experimental work, it has to be reported by the error analysis. If you do a numerical work, it has to be represented by the grid independent analysis. So as it is a experimental work here, this is the way you have to do the error analysis here. First, you need to find out whatever the primary quantities are being involved in your experiment. What are the derived quantities are being in primary quantity means you are going to measure it directly. Suppose you say voltage or current, these are measured very directly. But indirect measurement like Q, this Q you are calculating indirectly by the product of V into I. Similarly, H, transfer coefficient, convective transfer coefficient, all these are derived quantities. And you need to first identify what is the error in the primary quantities. Then you identify what are the derived quantities. Then you can use this error propagation formula. I think you must have studied somewhere in the course called thermal measurement. So by using this error propagation formula, you can find out the error associated with each quantity. And this is extremely important because the error has to be within a proper limit. Because if the error is extremely high also, then whatever the experiments you are going to perform give you the proper readings. So always you should maintain the errors in a what no, a specified domain. Okay. Now, this is a brief introduction about the kind of experiments. How do you do a laboratory scale experiment? Only two challenges: take a heater, take a heat source, and treat this as a heating block. Then you can do this what now other arrangements. mounted. This is my inlet condition, and along x direction the airflow is taking place here. We have gone to the mixed convection approach because I already told you in the beginning of the slides that mixed convection is highly preferable, because this takes care about both natural as well as the forced convection mode. And whenever is required, you can go to the natural convection mode. Whenever there is a required, you can go to the mixed convection mode. But how this mixed convection velocity has been considered here? The mixed convection velocity has to be identified by choosing that the temperature should not go beyond the safe temperature limit of 100, and all the mixed convection heat transfer modes are being quantified by a non-dimensional parameter called Richardson number, which is given as Gressup's number by Reynolds number square. So if you go to this approach, you can get that the mixed convection velocity equal to what now, 31 meter per second. So with the same 47 configuration, we have now carried out the numerical simulations by going to the proper governing equations as well as what now, boundary conditions. So you see, these are some of the fundamental governing equations you might have come across while you studied heat transfer convection. So this is my continuity equation. Continuity equation is only one because mass is a scalar quantity. There are three momentum equations because momentum is a vector, and there will be one energy equation. But I have added this extra term here because this is a mixed convection formulation, so that Richardson number part, that is basically Gressup's number by Reynolds number square, that had to be considered only along the flow direction, because if you just see the diagram, the flow is taking place along x direction. So along the x direction, that mixed convection velocity 31 per meter second, that need to be what now considered. Okay. Now these are fundamental governing equations all of you must have come across. But now coming to the boundary condition, these are extremely critical, because once you are not giving the proper boundary condition to your domain, and you might be thinking about a result, but a different result will pop up. So if you see about the boundary condition here, you see at the inlet what happens, your velocity is 31 meter per second and other velocities are 0, because you can see my velocity component along v and w equal to 0. Only there is a velocity of 31 meter per second along x direction, and also the temperature is what, 25 degrees centigrade. And on the outlet, what happens, the same temperature boundary condition cannot be applicable, because what happens now, when the chips are getting heated, the air will take away all the amount of heat. So the exit, you never know what kind of boundary condition it will be. Temperature boundary condition, it won't be ideal. So what you have to do now, you have to consider the pressure boundary condition at the outlet. This is quite common actually. I think some of you might have already doing the numerical modeling in electronic cooling. At the entrance, always this is temperature. At the exit, this will be always what, no, pressure. But apart from that, just to simulate the results from experiment, the all other sides has to be what, no, insulated. So here what happens, the chips are mounted only on the top of the plate. So, and there is a flow taking place along the x equal to 0 part. So all other sides need to be what, no, insulated. Then only you are going to get what, no, proper result. So on that note, the insulated boundary conditions has to be applied. Dou t by dou x, dou t by dou y, and dou t by dou z equal to 0. So these are some of the governing equations and boundary conditions need to be incorporated in your NCs, because we have done the analysis by using NCs iSpec, and this iSpec is being exclusively used for electronic cooling. And even the NCs will work out here, but if you go to the iSpec module, this is exclusively used for what, no, electronic cooling modeling. Now, once you have carried out the numerical simulation, you see this is my optimal configuration what we obtained. So in the previous slide, I have shown you the optimal configuration, how we have done by experimentally, and the same study is extended further, and we have obtained the optimal configuration. But if you see this optimal configuration, I got it for a lambda value of 1.58830, and here the maximum configuration temperature occurs for the smallest chip U2, which is around 78.44. Now as it is the smallest chip, what happens now, its heat accumulation rate is very high, because chip size is very small. You are supplying same heat input. If you just go to the heat input here, you can see U2 you are supplying around 5.46 watt per meter square, and also you see the size here, size is small among all the chips, and heat dissipation rate is high. So because of that, what happens, the heat accumulation rate of this chip is very, very high. So this suits to a higher temperature in the configuration, that is 78.44. But if you just do a comparison between the lowest lambda, my lowest lambda is My lowest lambda is 0.25103, highest lambda is 1.87025. When we made a comparison between the lowest configuration as well as highest configuration, you can see there is a difference of 15 degree, which is extremely important as far as the electronic component is concerned. So that means there lies a challenge of arranging the component properly, because as I told you that if there will be 10% reduction in the temperature, the lifespan of the electronic equipment is going to be half. So in that way, there lies a challenge for a proper optimal arrangement, because you can see that the lowest configuration is where the chips are very closely packed. If you go to the highest configuration, the chips are wide apart. So in that way, there is a gradient of 15 degree, which is extremely important as far as electronic cooling is concerned. But here you see, we got the maximum temperature is around 78.44, and we are not happy, because our goal is that you need to still control this temperature. So we have now moved from air to a different technique. So in our laboratory, we have gone to a new technique, and our goal is that to control this temperature. So same configuration we have considered, but only the technique we have changed. Initially, we have gone for air cooling, when we got the temperature to be around 78.44, but now we have gone to a new technique that is called HN material based technique, and this has helped us to reduce the temperature again drastically. So now let us try to go for the possibilities of PCM based technique. And you might have come across about this PCM also quite often. So Dr. Reddy, is it going fine? Am I audible to all of you?
Yes, it is everything fine.
Yeah. So as I told you that in the previous slide, my temperature was around 78.44, and this was purely air cooling. And now we want to reduce the temperature further. So what we have done, we have not disturbed that configuration. Same configuration we have considered, but only a new technique we are now going to follow, because our objective is to bring down the temperature. So we have gone to the PCM, phase change material cooling air. Why these PCMs are being used nowadays for heat transfer application? One important property is that high latent of fusion, because this can store enormous amount of heat. So the heat storage capacity for PCM is extremely high. Second thing is congruent melting. Congruent melting means the melting is uniform. So once you are use this PCM, this can uniformly going to reduce the temperature from all corners of the chips. And also this is recycled, because you are able to convert solid to liquid phase, liquid to solid phase, and this can be recyclable also. And this is very light. This is very light. Maybe I will show you in the next slide how do you do the characterization. This is very light, and chemically also this is stable. But only one demerit what the PCMs are going to give you, that this has got a very low thermal conductivity property, because you can see the thermal conductivity property of the PCMs here. If you go for N icosan as a PCM, it has got only 0.39 in the solid state, 0.157 in the liquid state. If you go for paraffin wax is nothing but your candle wax. I think this is quite familiar. Candle wax, whatever the candle we are using, the candle wax is nothing but paraffin wax. It has got the conductivity of 0.21 in solid phase. Liquid it is only 0.12. So because of this low thermal conductivity properties, this is not user friendly as far as heat transfer application is being concerned. So only PCM you cannot use here. The PCM can only be used in the integrated with the help of some thermal conductivity enhancers. So this TCE, thermal conductivity enhancer, is going to play a very important role to bring down the to maybe you can say to integrate the effect of PCM for the heat transfer application. So normally the aluminum is one of the best thermal conductivity enhancer, which has got a higher thermal conductivity of what, 230. So now whatever the PCM we are going to consider, they have to be now integrated with the help of what, no, TC. But the beauty of a PCM, what I told you, that high latent of fusion, you can see in equation 237.4 kilojoule per kg Kelvin, paraffin wax 173.4 kilojoule per kg Kelvin. So you can see the energy storage capacity. This will accumulate more amount of heat, and also you see the heat capacity of both N equation and paraffin wax, that is also extremely high. This is heat storage capacity also extremely high. And this is the melting point range. So depending upon the melting point range, depending upon the temperature requirement, either you can go for N-icosane, either you can go for paraffin wax. Because if you are going for N-icosane, once your system temperature will reach 36.5, the paraffin wax will melt. Sorry, the N-icosane is going to melt now. But if you go for paraffin wax, once your system temperature reaches up to 53, this will remain at solid, and then the melting process will start. So this is basically the working cycle of PCM. This is quite familiar. This is basically the phase transformation diagram where the solid is being converted into vapor. And first what happens, there is a temperature rise, then there is a melting phase. Then what happens, all the liquid is going to what, vaporized. Okay. So this is a simple cycle what you are going to come across as far as what PCM is being concerned. So these are some of the arrangements of PCM here. I'm not going to talk more details about this because Dr. Rajesh maybe tomorrow or day after tomorrow is going to talk about this in detail. But these are some of the arrangements you can find. These are known as plate type heat sinks, and these are fin type heat sinks. You can see there are multiple fins are being arranged here, and these are the multiple plates are there. But what is more important is when you go to the experiment, it is well and good. But if you go to the numerical model, these are some of the points you need to consider for the modeling of the PCM here. First, you need to consider what should be the size of the IC chips, what should be the size of the heat sink, how many number of fins you are going to consider, what are the size of the fins, what are the spacing between the two fins, what kind of PCM you are going to use, and the last point is extremely important, how much amount of PCM you are going to use inside a system. So these are some of the points or parameters you need to consider when you go to the numerical modeling part. Now, this is the way you can go to the proper modeling. All these details, I think he will speak in his part maybe tomorrow or day after tomorrow. So I'm just skipping this slide here because all these details will be covered by Dr. Rajesh maybe in couple of days. But what is more important here is I told you that PCM is going to store a huge amount of heat. Now the total enthalpy content of the system that is being given as a summation of sensible heat as well as what latent heat. Now this is the formulation because I think some of you or those who are already doing the PCM modeling, they might have familiar with this expression here. This expression will give you the sensible heat calculation. But what is most important in case of PCM is that initially this will be in solid state. Once you start heating it, slowly the solid PCM will start what now melting. So this alpha is basically what now the liquid fraction. It will be 0 if it is in a pure solid state. It will be 1 if the PCM is purely melted. Okay. So remember, alpha is the liquid fraction. So if it is pure liquid, alpha will be 1. If it is pure solid, it will be what now 0. And beyond that, that intermediate phase, the alpha can be defined as T minus T solidus divided by T liquidus minus part now T solidus. Okay. And these are some of the other arrangements also we tried in our laboratory. We have just kept the heat sink between the IC chips. We have also tried with keeping the heat sink on top of the IC chips, but that didn't work out. And the one more challenge also what we faced in the laboratory is that if you just go for a very simple arrangement or if you just go for a single IC chip, this heat sink arrangement will be extremely useful. But once you go for a multiple IC chip arrangement, when you try to keep that heat sink in between, this is not performing in a better way. So what we have done now, we have gone to the next technique by using the same PCM. We have gone to the PCM based mini channels or micro channels. These are found to be a better candidate, and also people have also done a lot of work on this mini channel based PCMs here, and this found to be extremely useful technique so that the temperature of the IC chips has been reduced drastically. Now I'm just going to talk about for a few more minutes about this PCM based mini channels. You can see the arrangements here. This is your initially substrate board where the chips are mounted, and this is the same optimal configuration what I obtained in my previous slides, because as I told you that we are not going to disturb the setup. So same optimal configuration I have considered. But now when you do the channels, you cannot do the channels in between the circuit board, because in between the circuit board there are electrical connections are there. We are not going to disturb that. So what we have done now, we have slightly extended the board. You can see the board is being extended, and on the outer periphery of the substrate board we have created the channels. and we have allowed the phase change material to flow across the channel, and there will be a continuous flow is being monitored. So how many channels are there now? There is a left channel, right channel. So maybe you can see this is left, this is right, this is top, this is bottom. So these are the channels we have considered, and also we have gone for various combinations: only left, only right, only top, only bottom, and also there could be a combination. There could be left, right, left, top, left, bottom. All the combinations also we have tried, and this is the computational domain we have considered. We have done both the experimental work as well as we have done the simulations here. And here also same mixed convection velocity. As I told you, we are not going to disturb the setup. So same mixed convection velocity we have supplied here, and we have allowed the PCM to flow inside the mini channels. And different cases we have considered. So case 1 will be only left channel filling. Case 2 will be only right channel. Case 3 top. Case 4 bottom. Case 5 combinations. All these combinations we have used. And both we have considered N-icosan and paraffin wax. N-icosan can be useful for low melting point, but for higher enthalpy and lower specific heat. Paraffin wax can be used for higher melting, lower enthalpy, as well as higher heat capacity. So depending upon the application, you can go for either N-icosan or what no paraffin wax. But only one demerit what we have observed is that the TC volume is very low. See, for our case, the TC is basically this aluminum board, and we found that the amount of filling of the PCM was extremely low. But anyhow, that was not an issue for us because we want at least couple of degree of reduction in temperature, because initially with air cooling we got it around 78.44, and we want that some amount of temperature has to be get reduced so that we can say that the PCM based mini channels are a better candidate. Now you see these are the combinations we have considered here. We have considered 12 different mini channel combinations. You can see this is only right, this is only left, this is top right, this is what now bottom right, this is left right, this is left top, this is what now left bottom, this is top right bottom, this is left top bottom, this is you can see left bottom right, this is you can see left top right, and this is left top bottom right. All the channels are being filled. So since we have identified around 12 different combinations, we have done the experiments, we have done the simulations for all the different configurations. First we have carried out the numerical model, and here you can see the multi-phase volume of fluid model has been used with this enthalpy porosity technique. This enthalpy porosity technique is being exclusively used when you want to model this what now PCM. So I think some of you might have already started using this ANSYS. You can say that this enthalpy porosity model has to be exclusively used when you are going to target these PCMs. And we have used now what this results in what no better cooling. So PCM is two cases actually we have considered. The case one we have considered without using the channels, and case two with using the channels, because we just want to have a comparison that how much enhancement you are going to have. So two cases the experiments were being concerned. One is without using the PCM based mini channels, and second one is with PCM based mini channel. But most of the PCM studies has been conducted for two parameters. One parameter is that you should look for temperature control. You should look that your temperature should reach around 85 degrees centigrade. Beyond that, you are not going to operate. The second, you should also look for able to achieve 100% melting. But here we have not gone for 100% melting, because as it is a experimental study, and as the channels are open on both the sides, if you go to 100% melting, the PCM can flow out, this can spill out of the system here. So instead of 100% melting, only 90% of melting is being considered. So two parameters now. One is the parameter to reach 85 degrees centigrade. Second is the parameter to reach 90% melting. For two cases, without PCM based mini channel as well as with PCM based mini channel. This experimental setup we have developed in our laboratory, and by using a wind tunnel as well as by using this PCM based mini channels. But the problem is that in the previous slide, I had shown you the melting points of the PCM here, but you just want to find out that whether your melting point is accurate or not. For that, you should go for the characterization study. This characterization study we have carried out in the National Chemical Laboratory, and the PCM, whatever we have used, initially we have used in the powder form. This is available in the market. If you just want to do the experiments, you can just bring out these powders and you can just fill in the many channels, and you can do this experiments. And once you have done the characterization, I think we found that this is almost a close match with the value whatever we have considered and whatever the characterization curve it has given. But of course, we have only gone for the heating cycle. We have not gone for the cooling cycle here. But if you just want to do the characterization for the cooling cycle, maybe you are going to get the similar results. And you can see here the same charging as well as the discharging cycle we have considered here. These are the different chips, and you can see if you just talk about chip number U1, chip number U3, U5, U6, U7, they take around 1000 seconds for charging, and then they have discharged here. But because of the high heat dissipation rate as well as because of the lowest size, you can see the chip number U7 as well as chip number U2, they take a longer time for charging as well as discharging. This also we have compared both charging as well as discharging cycle. And four cases we have considered. The four cases means the four different times to reach the 85 degrees centigrade. Case 1, 700 seconds it takes to reach 85 degrees centigrade. We have increased the time now, 944 second, 1292 second, and 2133 second. So the final one is basically 2133 second. Out of the total 2133 second, what we have done, you see, half of the time, like 945 second, we have considered for charging, and around 1168 seconds we have to see. Charging discharging is required because you want to regain to the same state again. Solid to liquid, you have to again come back to the same solid state. So we have gone to same charging as well as discharging. And what is the beauty? We found that the working cycle of the chips has been enhanced by 3.08 times. That is extremely important, because see, initially you just feel that because of this continuous operation, suppose your chips are going to fail in 10 seconds. Now by using the PCM based mini channel, it has been increased by 3.08 times. So same chip now can work for around 31 seconds. So that is the beauty. So instead of failing the chips by 10 seconds, now the same system can work for around 30 seconds. So that is the challenge actually, because you just want to improve the time, and so that you can say that the effective cooling can occur, there will be temperature reduction, and the reliability has been more important. You can see by using this PCM based mini channels, the reliability of the system has increased. And both the experimental and numerical results we have compared, and we found that almost they are going to match with each other. But of course, there was a challenge by carrying out the numericals, because when you deal with this enthalpy porosity model, the PCM you have to do it extremely in a decent fashion. Otherwise, there will be a much deviation between experimental. But here we found almost a good match between experiment as well as numerical results. And these are the temperature as well as volume fraction contours here. and you can see we have carried out up to 1000 second. Why 1000 second here? You can see the charging for most of the chips we have kept it at around 1000 second. And that's why this temperature contours, you can see that we started with 100 second. So each 100 we have increased, and once you have reached around 100 second, almost all the PCM has got what now liquefied. Okay. So we have observed this PCM melting up to 100 second. But what is the important consideration we find? We find that the reliability of the chips, the performance of the chip has been enhanced by around what now 3.08 times, and that's a good achievement we got in our laboratory. But again, as I told you, that the challenge was that the liquid fraction, the TC volume, it is extremely low because 2303 mmQ here. So for again low powered ICs, it is okay. But if you just think about a data center cooling like this, and it is extremely difficult to operate with a PCM. So I will just go to the last technique. I will not discuss in detail, but I will just give a few highlight about our work carried out in our laboratory. We have gone to the last technique. We have gone to the liquid cooling, and we find that this is also extremely useful to bring out the temperature of this IC chips. Okay, and you can see we have tried with air, which has got a boiling point of minus 193.2. We have gone with FC72, which is gone for 56.4 boiling point, and we have gone with water also 100 degrees centigrade, and we have seen that in water, you can see even if you go to the natural convection mode, you can go to a heat dissipation rate of 2.75 watt per centimeter square. If you go to mixed convection, you can see in comparison to air as well as FC72, you can go to a heat dissipation rate of 2.96 to reach to the temperature of what no 85 degrees centigrade. Similarly, if you go to a forced convection velocity also, to reach to the 85 degrees centigrade, water can be helpful to go to a heat dissipation rate of 102 watt per centimeter square. So looking to this picture, you can say that water is the best fluid to dissipate the heat from the components more effectively. Why it is so here? Because its boiling point is high. So at high boiling point, what happens? If you go to the phase transformation diagram, at high boiling point, what happens? The conversion from liquid to vapor will be much fast. So that length of that liquid vapor line will be extremely small. So the cooling will be much faster. But as all of you know that to take care of the liquid, to handle the liquid, or to design a liquid cooling system is extremely challenged, because just like that PCM mini channels, we cannot have a channel where you can allow the liquid to flow, right? Because liquid is going to be very conjurant as far as electric circuit is being concerned. Now what we find in our laboratory, we have gone to a new technique that's called a liquid cold plate technique. So we have designed this liquid cold plate in our laboratory, and we have mounted the electronic system on the top of the liquid cold plate. So now what happens? Now the electronic circuit board is not going to come in direct contact with this liquid here, because the liquid is going to flow inside this the liquid cold plate. Liquid cold plate is just like a heat exchanger arrangement. There will be multiple tubes will be there inside the plate, and this will help you to better temperature reduction. Now your entire system, like your printer circuit board with chips, all has to be mounted on the top of the liquid cold plate. Now this is the experimental setup we have designed in our laboratory, and it has different components. Like you can see, you have an inlet reservoir, because you need to supply the water to the liquid cold plate. Then there should be a pump will be there, because this will pump the water. You need to control the flow, so there will be flow control valve. There is a digital flow meter. This will tell you that how much amount of flow has been supplied to the liquid cold plate. Then there is a test section. I think this is not clearly visible. There is a test section consisting of liquid cold plate. Top of that there is a printed circuit board. Top of that there are the chips are being mounted. Then you need to supply, as I told you, that you need to supply heat to the chips here. So there is a DC power source. Then you need to record the temperatures by using a temperature data logger. There should be a computer, and again at the outlet there will be outlet temperature, outlet reservoir, where you need to collect this water. And we have gone for a different flow rates, low flow rates to high flow rates. And also we have gone for variable heat inputs 40.64 to 70.12 watt per centimeter square. Okay. So this mass flow rates you can convert into water velocity by using the formula m dot equal to rho AV. So this is a simple experimental setup we have in our laboratory. Okay. Now you can see this is the schematic representation, and also these are the points where you want to measure the temperatures, because you need to measure the temperatures of the chips, temperature of the SMPS board, temperature of the liquid cold plate, temperature of the insulations, temperature of the inlet as well as outlet temperature. So these are the places where we have connected this what now the thermocouples, so that you are going to measure the temperatures. But what beauty we have find here, see, when we have allowed the water inside the cold plate and we have not allowed the water, see, once you are going to allow the water inside the cold plate, you can see with experiment, my temperature was only 60. And without that, it has gone to what now? Around 110. Now, you see, still it has reduced now. See, first we started with air, then we have gone to PCM. Now, same module we want to execute by liquid cold plate. And you can see once there is a liquid water flowing inside a system, there is a temperature drop of around 20%. This is a significant temperature drop, because now the components are not in direct contact. You are just mounting on the top of the cold plate. This can be highly advisable for data center cooling. And you can see the configuration temperature, there is a drop of around 20%, and there is a temperature drop of around 50% when the water is flowing inside this water cold plate. So this is extremely advisable. So what conclusion we obtained here? And water, when this flows inside the electronic circuit, the liquid cold plate, this acts as a heat exchanger. It absorbs all the amount of heat, and now the chips are cooled at a what faster rate. Okay. These are some of the numerical study. You can see for higher heat input, the red color indicates that temperature is very, very high. Lower heat inputs, the temperature are being controlled. So this liquid cold plate is one of the best technique, you can say, to reduce the temperature of the ICCs more effectively. So most of the time now for data center cooling, what happens now, the data centers are being kept on a liquid cold plate, because all of you might have studied in thermodynamics as well, in second lab thermodynamics. The heat sink, what they are going to do now, this will absorb the heat and this will dissipate to outside. So this liquid cold plate, this will now dissipate the heat and this absorbs to the outside. Now, as Professor Balaji pointed out in the inaugural session, because of this, there is an environmental effect, there is a formulation of global warming. But now the challenge lies is that maybe I think all our young engineers, we can also think about it. Whatever the hot water comes out actually, now we should think about a way to use it very effectively. So there is also a lot of research work is being going on, where there should be effective utilization of that heat exit, so that the global warming efforts can be saved. So this is my brief presentation here, and I'm just summarizing this. So maybe in the first couple of slides, you find that the configuration maximum temperature, this is a strong function of IC chip size, how they are placed on the board, what kind of working fluid you are using, and what is their heat dissipation rate. And also we find that the highest lambda value leads to the optimal configuration, and the high heat element that has to be placed in the substrate bottom, because once you are placing at the bottom, because of the convection, this has to be cooled fast. And we have gone to the robust optimization technique, that ANN GA-based technique, and this has helped us to predict the optimal configuration of the chips. And then we wanted to reduce the chips temperature more effectively, so we have gone to the PCM based technique, and it has increased the working cycle of the chips more effectively, because you can see there is an enhancement ratio of 3.08 times. If you go for N-icosan, it has slightly got a lower melting point, but this will help you to reduce the temperature of the IC chips effectively. But if you go for a higher specific heat paraffin wax, this will help you to store the maximum amount of heat. So depending upon the application, you can either go for N-icosan and paraffin wax. Both are commercially available in the market and easily available. So if you just want to start an experiment, maybe you can just think about both these candidates. And by using the PCM best, we can say that I already mentioned it. The working cycle has enhanced between 2.33 to 4.6 times. So PCM is basically a better candidate for significantly reducing the temperature. Okay. And we have gone to one more technique, that is called liquid cold plate. When the water flows inside it, this is able to reduce the temperature by around 20%. And why is it so? Because the liquid cold plate, this acts as a heat exchanger, and this helps to reduce the temperature of the high heat generation chips effectively. So in total, if you go for a hybrid technique like liquid cold plate, PCM, air, so these are some of the challenges in thermal management, and this will lead to a better reliable system, because they are going to significantly reduce the temperature of the electronic components, and ultimately the components are going to be cooled at a what no faster rate. Okay. So I have just given a introduction about a few techniques. Maybe now if somebody is interested, they can try some of the techniques, and you can also bring out a laboratory scale experiment in your institute. You can also try some of the optimization techniques, so that you can bring out with a good amount of research work. Okay. So thank you very much. If you have any doubt, you can ask me now. Thank you.
No, chat box. Sir, how do you arrive on?
Somebody is asking how do you arrive velocity of 31 meter per second for numerical simulation. So as I told you that the mixed convection velocity has been mixed convection is being characterized by a parameter called Richardson number, and Richardson number is gr by r square. Gr formula you know from heat transfer, g beta delta t L square by nu square, and Reynolds number equal to rho Vd by nu. Okay. So by doing this formulation, you can get that velocity, because for mixed convection, your Gressup's number is basically 1. So you take that ratio to be 1, then you can get that velocity. And we got it around 31 meter per second, looking to our size as well as heat dissipation requirement. If your size is different, if your heat dissipation requirement is different, then you can get a what no different velocity. Okay. So I hope that you got the point.
Any more questions from participants? Could you share PPT?
Yeah, maybe I will give it to Dr. Reddy, and finally he will consolidate it, and he will send to all of you.
Yes, yes. Okay. Any more questions? Okay. Thank you, Dr. Tapan, for your excellent presentation on hybrid cooling techniques. Thank you for accepting our invitation and attending for this session. You have given very good presentation. Uh, from participants, if you want to give any feedback, you can talk.
So somebody is asking, all the results were taken from NC Splint. See, first of all, we have not used NC Splint, we have used NC's iSpec. But of course, both are same, because iSpec is basically an electronic cooling module in NC's. And we have done both experiment as well as a numerical simulation, because experiment is a benchmark. Whatever the strategy I have used, maybe by using the same strategy, you can create small laboratory scale experiments in your institute as well. So then you may compare the results with NCC. But nowadays, experiment is benchmark. You should be good in experiment, so that you can just compare the results by using the NCs. Okay, so that's what I say.
Okay. Thank you, Dr. Tapan.
Yeah. So thank you, sir. Thank you, Dr. Reddy. Thank you very much. Okay, I'm signing off. Okay, thank you.
For participants, I shared session 1 feedback form and session 2 feedback form. Please fill those. Based on this feedback, those who are filling the feedback form, we will give certificate for participation. I request you, please fill this. Thank you. And afternoon, Professor C. Balaji from IIT Madras, she will address the participants on issues and handling of electronic cooling equipment. Okay, I request you all, please participate in the afternoon session by 2:45 p.m. It will start by 2:45 p.m. and by 3 o'clock sir will join. Okay, it will be 1.5 hours. If you have any questions, you can ask me. Yeah, if there are no questions, we can leave. Thank you for all.